Hi, welcome to your lesson on domain and range. This is a very big idea in mathematics. Let's get into it. We're going to begin with the vertical line test. Notice that both of these graphs have a vertical line in blue. We're going to talk about what that vertical line was going to do for us. Basically, for graphs of relations, we're going to use the vertical line test. If the vertical line hits twice, then what we have, our relation is not a function. We know the definition of a function is a relation where each input leads to only one output. So let's see what the vertical line does. If the vertical line hits twice, for example here, I think this vertical line as we move it may hit twice here. Let's check. Every time it hits our relation twice, I'm going to make a beeping sound. Let's try here. Okay, there goes the vertical line. Beep. Okay, you noticed right here it hit our relation twice. That means for that single input of 1, we had two different outputs. So the vertical line, by hitting twice, is telling us there's multiple outputs for one input. So this is not a function. Now let's move the vertical line across this one in just a moment. Let's summarize that. This is only a relation then. One input value gives two outputs, therefore not a function. This one, let's try the same thing. Move the vertical line across. And I heard no beeping. I hope you didn't hear any beeping either. It never hit the relation twice. Therefore, every input has only a single output. So, over there we have a relation, which is also a function, because each input value gives only one output value. So the vertical line test is a nice visual way to quickly check if our relation is a function when it's in graphical form. Let's try it on this problem, which should look familiar. We have the entire Timberwolves NBA basketball team. The entire team here, and over here are different ages, and over here are average points. So what that means is, since this is the whole team, these are the different players and all their ages. So we have players from age 27 to 34. There's a couple players that are 29, and there's two players also that are 28. And on this y-axis we have the average points they scored. So over a season, or over when they were that age, they had some average points from game to game. And you can see, for example, the two 28-year-old players, one of them had an average of 8 points per game, and the other one had an average of nearly 25 points per game. But the point is, you have multiple players here that can be the same age. So let's do the vertical line test. Beep, beep. All right, you heard the beeping. Definitely. The vertical line hit twice here, and it also hit twice here. That means our relation is not a function. And that makes sense, because we can have multiple outputs, multiple point averages for a single input, for example, 28. That makes sense for the whole team. Over here we have just Kevin Garnett, a single player, and age. So over his different ages, when he was 20 and 22 and 24 and so on, what was his average points per game? And let's try the vertical line test. Definitely heard no beeping there, and that should be definitely the case there, because if we heard beeping, it would mean that at one age he would have two different averages of points, and that's impossible. This is one person; they can only average a certain number of points. So this is definitely a function. Okay, let's check these we have here. It is a function. This one, not a function. We can see vertical line hits the relation twice, therefore one input leads to two different outputs, not a function. How about these? A, B, D, and E, which ones are functions? Let's check. A, never hits twice, great. B, also never hits twice. D, nope, never hits twice. And E, it follows that horizontal line but never hits twice. Great, they're all functions. How about these three? C, F, and G, which are functions? C, beep, 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 beep. Oh, wow, it's hitting twice all the way along. How about this one here? Beep, 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 beep. Also hitting twice all the time. Not a function, not a function. This one, how about this one? There, it's hitting the function there. Okay, so here's the function. It is this line that looks like it's almost straight up and down. If it was straight up and down, we would have a 90-degree angle though. There's not a 90-degree angle there. If this was 90, then this vertical line would like rest perfectly across the whole line. That means it would be hitting at every single point on the line if this was 90 degrees. But this is 89. That means it's slightly diagonal. Just a little bit, but it is. So imagine it was diagonal like this, then this would only hit twice, only once every point. So therefore it is a function. Okay, let's look at the next thing. So now we're going to talk about domain and range. Domain and range. Let's say you are given a relation like this. So here's a relation given as a set of points. So it's a limited set of points. There we have it. What's the domain? Well, as you may remember, domain is all the input values. In this case, domain is the set of these points. Here's our inputs, 1, 5, 2, and 5. We only have to list 5 once. So what's our range then? It's the set of numbers, the output numbers, -6, 3, 4, and 7. So those are outputs. Okay, that's a simple example of domain and range. We can just take it from a set of numbers. But what about if we have a function, a graph, and this graph goes, it has infinite points. So how do we represent domain and range when it's infinite? Well, we talked about that in the last lesson. We can represent infinite sets using different notations like interval or set notation. So domain means, again, all the x values, and range means all the y values. So here, all the x values, let's say this was 3 and 11, and let's say on this axis we had 9 and 20, then our domain would be all these numbers between 3 and 11. So for domain, we would say x is between 3 and 11. Of course, we can be more precise because this open circle means not including 3, and this closed circle means including 11. So our domain in set notation could be like this. X values such that x is greater than 3 but less than or equal to 11. Notice the equal here because we have a closed circle, and notice no equal sign here because of the open circle. So basically x is between those values, but it includes 11. That's our domain, all those x values. In interval notation, you may remember we can use a squared bracket turning out to represent not including 3, so from 3 to 11, including 11, but not including 3. And the other way of writing interval notation, instead of using the outwards turned square bracket, we talked about using a rounded bracket. So from 3 to 11, not including 3, including 11. So that's our domain, all those x values. All those infinite points between there can be captured in these single statements. How about our range? Well, our range is all the y values, so y is between 9 and 20. Again, we can be more detailed than that. We can say not including 9 and including 20 because it goes all the way up to 20 here. So in set notation, y such that y is between 9 and 20. We can see y is greater than 9, but y is less than 20. So greater than 9, less than 20. So y is between those numbers. And here we can see no equal sign, and here we can see equal sign because it includes 20. Whether you're considering this the high point or this the high point, there's a point that exists right there at 20, so it includes 20. And in interval notation, we can write it like this. From 9 to 20, not including 9, but including 20. Or from 9 to 20, not including 9, including 20. Okay, that's a recap of something we did in a recent lesson, but now we're looking at it in the context of domain and range. So let's take some notes. First thing, there are two types of data we're going to encounter, discrete and continuous. Discrete data is separate, distinct points, whereas continuous data is graphed as lines or curves. And then domain and range, just to have those one more time, domain is all the possible values of the independent variable, or the x values, and the range is all possible values of the dependent variable, or the y values. Here's some discrete data, here's some continuous data. Notice this is discrete, it's single points. Here's continuous, it's many points, it's infinite points, all connected with a curve, that's continuous. And here, for this one, we can say the domain then, since it's discrete, we can list all the values in the domain. 2, 4, 6, 8, all the possible x values are listed here in this set. The range here can also be listed. It's these specific y values. It's the specific y values that these points take on. And the whole set is there. For continuous, we just talked about it, we need to show it as a set of infinite points. So therefore, x values between 5 and 40, so between 5 and 40, including both. And range is all the y values from 2 to 11, 2 to 11, including all the points, showing it like this. Okay, that's domain and range. A lot of students struggle with domain and range, so I'm just going to highlight it here using these colors. So for domain, I'm going to use the blue. So domain begins here. Always begin here. I'm going to extend this. The domain goes to here, but actually you see this arrow here, so that means that this will continue forever diagonally in this direction. So I can just show the blue going all the way to infinity, because this will keep going, going, going. But definitely the domain begins here. So if you were to express that domain, you would say from -3 all the way to infinity. right? Now let's talk about the range. The range is the y values. So if I take this red thing, where do the y values begin? I'm going to drag this up. Well, the y values begin here. There's no y values below there. The graph does not exist down there. And now it can be all these y values, right? The graph goes. And then, even though the graph ends right here, again, there's an arrow here. So this will go up forever. That means the possible y values for this graph also go up forever like that. So the y values begin, looks like -4, and they go all the way up to infinity. So that's domain and range kind of made more visual. Let's take a look at that one by actually filling it in. So here we are. What's the domain? And let's use all three notations, set notation and then interval notation. So in this case, domain is like this. Like we said, it begins at -3, and then the domain of this graph continues in this direction all the way, and this is an arrow, so positive infinity. So -3 to infinity. That's our domain. And we have not including -3 because it's an open circle, and also not including infinity because we can't include it. All right, domain written in interval notation, -3 to infinity, or -3 to infinity, not including each one. Okay, range. What's the range? The range is y such that all the y values with this condition that they begin at -4 and they go all the way to positive infinity. Again, the y values begin here and we can go all the way up to get all the y values here. -4 to infinity, including -4 because the vertex is right there. That point exists, so -4 to infinity. In interval notation, -4 to infinity or -4 to infinity like this. Pause there if you need to. A lot of students struggle with domain and range the first time they see it on a graph like this. Make sure you understand exactly how this works. Okay, how about this one? Domain and range. Let me do the same thing with the blue bar. Domain, well, what x values does this graph cover? Again, there's an arrow here and an arrow here. That means it will forever keep going diagonally this way and diagonally this way. So eventually, if you keep following this forever, it will cover all x values to -infinity. And in the other direction, same thing. So the domain, I'm going to go beyond the graph here, saying it's going to go to -infinity and to positive infinity, both directions. And the red one for range, well, same thing here. This goes down forever and up forever. So eventually all y values will be covered by that graph. So positive to -infinity for sure. Okay, so domain for this one is x values from -infinity to positive infinity. In set notation, we see it like this. Okay, because this graph will eventually cover all x values in the negative direction and all x values in the positive direction. In interval notation, -infinity to positive, or negative to positive infinity with the outward turn square brackets, meaning not including. And this also means not including. How about the range? Range is the same, exactly the same. -infinity, negative y values all the way to positive infinity y values. It goes, all the y values are covered up and down, so like that. Or we can write it interval notation, -infinity to positive infinity, or like this again, negative to positive. So in this case they're the same because the graph continues forever both ways. This one's a little different. Let's take a look together. First, I want to fill in this dot instead of open circle, closed circle. Second, look at the graph here. As it approaches x equals 1, notice it seems to go straight up, as if there's like a wall here keeping it from passing that point. Well, there is a wall. In mathematics, we call that kind of wall an asymptote. So here we have a vertical asymptote at x equals 1. That means the graph will approach that wall forever but never pass it. So it's kind of locked in position there. So when we do the domain and range, first of all, for domain, we can say, okay, well, the domain, the graph goes, x values go up to 3. They don't go beyond there for sure. So that's the limit of the domain there. And then the domain going the other way is limited there. Again, the graph hits a wall. So x values can only be between there and here. Okay, that's the x values domain. Now let's talk about the range. The range, well, I can lift it all the way up here because y values begin here. The graph doesn't exist below that. And then the y values go up, 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 forever up because there's an arrow going up. So they begin here and they go forever up. Okay, let's take a look at that in terms of our domain and range. So here we have that asymptote again. And now domain, x values from 1 to 3. And including 3 because I shaded in that circle, but not including 1. When there's an asymptote, you don't include it. So x values can be between 1 and 3 only. Shown in interval notation looks like this. 1 to 3, and then range is from -1 all the way to infinity, and it can be shown these two ways as well. Pause this and study this one closely.